Welcome back, ladies and gentlemen, to another exciting AP chemistry video. Now, I first want to apologize for the sound in the background. My next door neighbors decided now is a really good time to weed eat, and I decided now is a really good time to make a YouTube video. So the two things don't necessarily go very well together, but we're going to have to try to make the best of it. We are still focused in Unit 1. Today our focus is going to be on atomic structure and electron configuration, so getting a real strong understanding of how atoms are put together and their electron structure is absolutely crucial to understanding things like ionization energy, atomic radius, and the other components in this unit, including things like chemical bonding. So we're going to dive right in and see just what this unit has to offer us. So let's go ahead and take a look at our learning objectives for this part of the unit. We'll look at what the College Board has to say here in just a moment. But the very first couple things we want to look at here are that atoms and molecules can be identified based on their electron distribution and energy. So electron configurations, as you've probably studied before, they're very unique. They're unique to atoms. Ions will have different electron configurations, etc. The atom in and of itself is composed of negatively charged electrons and a positively charged nucleus that is made up of protons and neutrons. The negatively charged electrons are in an electron cloud or orbital. It's a three-dimensional space that surrounds the nucleus where we're likely to find an electron. You may recall that that differs significantly from the Bohr model, which has electrons just orbiting around the nucleus, very similar to planets orbiting around the sun. Coulomb's law is used to calculate the force between charged particles, so we'll be talking a little bit about Coulomb's law. Now, you will not have to do any Coulomb's law calculations, but we will be discussing Coulomb's law in terms of magnitude of charge, distance, and attraction between positively charged particles and negatively charged ones. In atoms and ions, the electrons can be thought of as being in shells, energy levels, and subshells, which are known as sublevels, as described by the electron configuration. Inner electrons are called core electrons, and the other electrons are called valence electrons. These are the ones that are involved in chemical bonding that you may have learned in previous years in chemistry. The electron configuration is explained by quantum mechanics, as delineated by the Aufbau principle and exemplified on the periodic table. So you're not going to need to know anything related to the quantum numbers in and of themselves, but you will need to understand electron filling rules, Aufbau principle, Hund's rule, Pauli exclusion principle, those types of things as you write and make your electron configurations. And lastly, well, I think it's lastly, who knows, but the relative energy required to remove an electron from different subshells of an atom or ion from the same subshell in different atoms or ions can be estimated through a qualitative application of Coulomb's law. So we're going to be thinking about Coulomb's law as we determine the amount of energy required to take away an electron. We need to think about how attracted that outermost electron is to the positively charged nucleus. And again, we'll dive into Coulomb's law and have that discussion in just a moment. This energy is related to the distance from the nucleus and the effective charge of the nucleus in and of itself. So again, let's go ahead and dive into the nature of atoms in and of themselves. Atoms are composed of protons, neutrons, and electrons, and you should already be at least somewhat familiar with this. Protons have a positive charge, electrons have a negative charge, and neutrons are neutral. Protons and neutrons are found in the nucleus, and electrons exist in three-dimensional regions around the nucleus called orbitals. You may notice here you have a variety of different orbitals, 1s, 2s, 3s. Notice that the size of the orbital gets larger in terms of its volume as you get further away from the nucleus or increase in energy level. So the higher the energy level of that orbital, the larger that particular orbital is. Now, in terms of the different number of neutrons and electrons, remember that the proton number is the one that determines the element that's on the periodic table, such as there's always going to be one proton in hydrogen, two protons in helium, three in lithium, etc. But remember that atoms can differ in the number of neutrons and electrons. If they differ in the number of neutrons but have the same element, they're known as isotopes. So hydrogen, for example, could have one proton and one neutron, or one proton and zero neutrons. They're both isotopes of hydrogen, that they're referred to as isotopes because they differ in the number of neutrons. And then remember that ions are the same element but different number of electrons, so they have either gained or lost electrons depending upon what charge it's taken. And remember that ion charges are often found as a periodic table trend, and you've probably labeled the top of your periodic table with these quite a few times as you've gone through and done nomenclature. So if we look at the very first column there, everything in that first column has one valence electron. It wants to get rid of that valence electron. So when it does, it has one more proton than electron. And so it takes a positive one charge. Everything in that second group loses 2 electrons, so it will be a 2 plus charge. And you can see some other general trends that are found on the periodic table. Again, these are things that you should already know. If not, you may want to go back and take a look at one of my other videos that's related to nomenclature to really get an idea about this. But understanding these charges is really, really important when we do nomenclature, when we determine the formulas of chemical compounds based off of their names and the ions from which they are formed. So as we mentioned before, electrons exist in shells, and the shells are referred to as energy levels. Those are essentially the periods number that's on the periodic table, so 1, 2, 3, 4, 5, 6, etc. High energy levels indicate that the electrons tend to be further away from the nucleus. Again, we can't tell the exact location of an electron. It's unknown where that electron is located, but we have kind of a good guess as to where it's located based on the size of the orbital in and of itself. And then we can describe the location of these electrons using what's called an electron configuration. Essentially, think of it as an address, a postcode, if you will, in order to tell where those electrons in an atom or ion or isotope are exactly located. So a couple things to keep in mind about electron configurations. I'm going through this a little bit quickly because the expectations, you already know at least a little something about electron configurations. I know for my group, this is actually their 3rd year of chemistry. So I know they've got quite a decent background in electron configurations and understanding how these are put together. Again, if you are completely lost on electron configurations, I would highly recommend you go and take a look at another video on my channel. Just search electron configurations on my channel. I'm sure you'll find one or many videos that correlate to that. But each electron in an atom is given a series of letters or numbers based on its location. So energy levels are on the left-hand side. If you look at the periodic table, you've got period number 1, 2, 3, 4, 5, 6, 7. Those are referred to as energy levels. And then we have blocks of sublevels. So notice that the first and second group are referred to as the S block. You can throw helium in there as well. The last 6 groups are referred to as the P block. The middle 10 are the D block, and the bottom 14 are referred to as the F block. We'll use these when we go through and determine electron configurations. Remember, we write out the energy level, sublevel, and how many electrons are in that sublevel. The maximum number of electrons is the maximum number of elements wide the sublevel is. So as we go through and count these out, S sublevel can have a maximum of 2 electrons, P 6, D 10, F 14. So for example, hydrogen's electron configuration is 1s2. It refers to the fact that it has 1 electron in the first energy level and in the S sublevel. Helium is 1s2. It has 2 electrons in the first energy level and in the S sublevel, and so on. If the element is beyond a sublevel, we assume that it is full, so we use the periodic table kind of like a board game, going in order based on atomic number. So for example, if I look at sodium, sodium is number 11 on that periodic table. It's going to end in 3s1 based off of the fact that sodium is in the 3rd energy level, it's in the S sublevel, and it's 1 group in that S sublevel. Because it's past the 2p, the 2s, and the 1s, it's considered full. So we write out the electron configuration as is. A good little hint here is that if it is a neutral atom, that the number of electrons, the exponents in your electron configuration should add up to equal the total number of electrons in your atom, or add up to your atomic number. You can look at it either way. Now, if it's an ion, a little bit different story because they have gained or lost electrons. D block, however, a little bit different. We are going to subtract 1 from the energy level, and F block you subtract 2. So notice that when I do bromine and I get to 4s2, which is kind of where that potassium and calcium are located, we don't go from 4s2 to 4d. It goes to 3d. And that has to do with the fact that that D sublevel is actually pulled in closer to the nucleus. So it's considered to be in the 3rd energy level as opposed to the 4th energy level when we do our electron configurations. Again, this is just a brief overview of electron configurations. Don't think that this is all there is to it. If you need some extra help, check out one of my other videos, and I'll be more than happy to help you out that way. Keep in mind that when we have ions and we want to represent them with electron configurations, we need to take into consideration the charge that's associated with it. So if I look at this example here, I have sodium, which is represented by 1s2, 2s2, 2p6, 3s1. If it has a positive charge, it means it has lost an electron, so we remove the electron or add electrons to the outermost sublevel. Don't be taking them away from ones that are core electrons. You're going to add or remove them from the number of valence electrons. Those are the ones that are the outermost electrons in your electron configuration. So we remove it from the 3s. If sodium for some reason had a negative charge, we would be adding it to the 3s and then to the 3p, etc. So make sure that when you remove or add electrons, you're removing them or adding them from the outermost sublevel. Electrons that are in an excited state, so if you've gone through and talked a little bit about quantum theory and understanding how atoms jump an energy level, and when they get into the excited state, and then when they go back down to the ground state, they release that energy as light. So basically, if you've ever done any flame testing before, you're familiar with excited state electrons and how they work. Well, in this case, we have sodium in its normal state, but notice its excited state, it looks a little bit different. An electron has jumped an energy level, so you're going to find that they don't follow the normal pattern of electron configurations. So if I see the excited state here of sodium, it goes 1s2, 2s2, 2p6, and then jumps to 3p1. So the outermost electron that was in the 3s sublevel has jumped to the 3p sublevel. So that's how we know something's in an excited state, is if it doesn't follow the normal pattern of an electron configuration. Keep in mind that we can also use noble gas notation to represent electron configurations. This is very simple to do. We simply replace the electron configuration of the last noble gas that we passed as we wrote our electron configuration. So again, I'm going to use sodium as an example. We write sodium as 1s2, 2s2, 2p6, 3s1. Well, the noble gas that's closest to sodium, or the one that we most recently passed, is neon. Like I said, we go backwards to figure that out. So we put neon in brackets, and what that does is that represents the entire electron configuration up until we get to neon, and then we just write what's left over. Remember, it's the last noble gas I passed, so even if I'm at chlorine or even argon, which is a noble gas, we still write our noble gas notation with the previous noble gas. So if it's chlorine or argon, we're going to put neon in brackets and then finish out the rest of the electron configuration. So let's dive into a very important concept that's related to chemistry, and this is something that I reiterate to my students very frequently and very often, is the concept of Coulomb's law. I always state that if you understand Coulomb's law, you truly do understand the concepts of chemistry. And Coulomb's law is very straightforward. There's a force of an attraction between a positive and negative charge, and the force of attraction is related to two specific things. The force of attraction is related to the magnitude of the charge, that is how strong the charge is, and it's related to the distance between the charges. So I'll be referring to the charge of the nucleus when we do this for the most part, because the nucleus carries a positive charge, and I'll probably refer to that as nuclear charge, which just explains the attraction of electrons to the nucleus. So if we have an increased nuclear charge, there's greater attraction. But long story short, Coulomb's law is very straightforward. Like charges repel. Two things that are negatively charged are going to repel one another, and things that are oppositely charged, a positive and a negative, are going to attract one another. The relative strength of this attraction is related to two factors: the magnitude of the charge, that is how positive and how negative those two charges are, and the distance between those charges. If you're familiar with physics, the equation on the right probably looks very similar to the law of gravitation, which works in a very similar way. It just refers to the masses of the objects rather than charges. But you can think of them in a very, very similar way. So knowing Coulomb's law, as I mentioned before, very, very important to knowing many different concepts that are related to chemistry. So let's take a little time differentiating between core electrons and valence electrons, and the challenge it is to remove the core electrons when compared to that of the valence ones. So the innermost electrons are called the core electrons, and these can be very, very difficult to remove. So if I look at silicon, for example, the outermost energy level is the third energy level. So we have 2 valence electrons in the 3s sublevel and 2 valence electrons in the 3p sublevel. All the rest of the electrons are in energy levels that are much closer to the nucleus and are going to be much more difficult to remove. This goes back to Coulomb's law. We have to keep in mind that the nucleus of an atom is positively charged, while the electrons are negatively charged. So there's going to be some attraction there. Well, remember with Coulomb's law, the closer those electrons are, those negatively charged electrons are to the positively charged nucleus, the greater the attraction there is. So there's a lot of ease in removal of valence electrons because they are the electrons that are further away from the nucleus. They are the electrons that are least attracted to the nucleus and therefore are easier to remove. The core electrons are more challenging to remove because they're closer to the nucleus and have a greater attraction due to Coulomb's law. Look at germanium, for example. You have 4 valence electrons in the outer shell as well. The 2 valence electrons in the 4th 4s sublevel and 2 valence electrons in the 4p sublevel. That 3d sublevel is close to the nucleus. We would consider it a core set of electrons. So we need to think about these things in regards to the ease of removal of an electron. Core electrons are going to be difficult to remove because they're much closer to the nucleus than that of the valence electrons, which are the ones that are furthest away. And we use the term ionization energy to describe the amount of energy that is needed to remove the outermost electrons of an atom. The amount of energy needed is directly correlated to the strength of the attraction between the outermost electrons and the nucleus. So you can really think about which electrons are going to have the higher ionization energy. It's going to be more difficult to remove the core electrons than it is the valence electrons. So therefore, the core electrons are going to need more energy to remove them, thus a higher ionization energy. As we mentioned before, the electrons that are further from the nucleus are going to experience less nuclear charge. They're going to experience less attraction to the nucleus due to their distance from the nucleus, making those electrons easier to remove. So when we compare elements in a group, the one further down will have the easier electrons to remove because those valence electrons are at an energy level that is further away from the nucleus. Take a look at lithium, sodium, and potassium. The outermost electron in lithium is much closer to the nucleus than the outermost electron in sodium. So therefore, sodium is going to have a lower ionization energy. It's going to be much easier to remove the electron from sodium than that of lithium because it's further away from the nucleus than that of lithium. And so as a result, it has a lower ionization energy. So as that outermost electron shell, the valence electrons become further away from the nucleus, it becomes much easier to remove those electrons. So I have a practice problem here I'd like you to take a minute and think about. And use the concepts that are related to Coulomb's law to explain which is more likely to lose an electron, sodium or potassium, and justify your answer. Take a few moments to do that, and then I will be back with you for the answer, and we'll move on. All right, so hopefully you paused yourself, gave yourself a little bit of time to think about this question. I typically frame these things in terms of claim evidence reasoning. If you're unfamiliar with that, maybe that's a YouTube video I can post a little bit later on. I'm not really sure. Hey, future content, exciting. But for this, it just says which is more likely to lose an electron, Na or K. So if I'm going to use claim evidence reasoning for this, my claim is going to be that K is more likely to lose an. I'm going to abbreviate here just because of space. Do not abbreviate on an AP exam, dear God. But K is more likely to lose an electron than Na. This is due to the valence electrons in potassium being at a higher energy level than that of Na. So you see here, I'm comparing and contrasting, right? I'm using both as I go through and create my answer. So this is due to the valence electrons of K being at a higher energy level than that of Na. Valence electrons at a higher energy level require require, promise that's what it says, require less energy to remove. Thus, it is easier to remove an electron from K than Na. Okay, so I know that there's a lot that's written there, and in all honesty, it's probably kind of hard to read, but I think you get the idea of what we're looking at here. Make your claim, K is more likely to lose an electron than Na. Provide your evidence. Your evidence is rooted into Coulomb's law. An electron that's further away from the nucleus is going to be easier to remove. You can even reference Coulomb's law in this. You can state that it's less attracted to the nucleus due to the greater distance between the nucleus and the valence electron. I mean, there's tons of different ways to go through and describe this, as long as you're referring to the fact that the valence electrons in potassium are at a higher energy level than that of Na. and therefore are easy to remove because there's less attraction due to Coulomb's law, you should be in good shape. All right, so that would be an appropriate response to this. Let's move on and see what else we have for today. So we've done our comparisons going up and down a group. How do we compare the strength needed, or the amount of energy needed to remove an electron when we're in the same period on the periodic table? And this directly correlates to Coulomb's law again. In the same energy level, the amount of energy required to remove an electron increases as you go left to right because the number of protons increases in the nucleus, thus making the outermost electrons more attracted to the nucleus, increasing the nuclear charge. So if we think about it, electrons that are in the same energy level as you go left to right across the periodic table are going to be more attracted to the nucleus, and that is because the nucleus gains more protons. If you look in the left side, or sorry, look on the right side here, you notice that you are increasing in the number of protons going left to right, 3 protons, 4, etc., going up the or going across the periodic table. So because there is a greater magnitude of charge in the nucleus, we're going to experience greater attraction of those outermost electrons to the nucleus, and thus a higher ionization energy is needed to remove them. So it's a little different when we go up and down a group. We're comparing the distance from the outermost electron to the nucleus. Here what we're doing is we're comparing the magnitude of the charge of the nucleus and seeing what's going to have a greater attraction. 3 positive charges is going to have less of an attraction to that outermost electron than 4 positive charges. The magnitude of the charge of the nucleus increases going left to right, and thus the ionization energy, it increases. So the rationale or the evidence you're going to utilize when you do claim evidence reasoning is going to differ depending upon whether you're comparing elements in the same group or in the same period. If they're in the same period, utilize magnitude of charge as your justification. If they're in the same group, you're going to use the distance of the outermost electrons being in a higher energy level, being further away from the nucleus, and so on. So you need to think about these things when you write your free response questions and when you do claim evidence reasoning in regards to Coulomb's law when comparing ionization energies. So just like before, I'm going to do a practice problem here. It's asking you to compare potassium and calcium in regards to Coulomb's law. We'll take a couple minutes and go through and try to write a good free response question or free response answer to this, and I will bring you back in just a moment. So here we go again with a very similar question. Which is more likely to lose an electron, potassium or calcium? Or you could say which has the higher ionization energy, which has the lower ionization energy. Just make sure you read the question carefully. But this time we're comparing potassium and calcium. Well, in this case, they're both in the same period on the periodic table. So that means we need to compare them in terms of magnitude of charge. Potassium is going to have 19 protons in the nucleus, whereas calcium is going to have 20 protons in the nucleus. So the one that's more likely to lose an electron is going to be potassium. So in this instance, I would say K is more likely to lose an electron than calcium. This is due to the valence electrons in potassium experiencing less attraction to the nucleus due to a smaller magnitude of charge in the nucleus of K when compared to calcium. This means it requires less energy to remove an electron from K than Ca. Thus, K will be more likely to lose an electron. Wow. Started off strong, but man, towards the end, my hand started to cramp there. But I think you get the idea here, so I'll read that to you one more time. K is more likely to lose an electron than calcium. This is due to the valence electrons in calcium experiencing less attraction to the nucleus due to a smaller magnitude of charge in the nucleus of K when compared to Ca. This means it requires less energy to remove an electron from K than Ca, thus K will be more likely to lose an electron. So again, I'm very, very deliberate in explaining not only the attraction, but how that correlates to Coulomb's law. In fact, you can even use Coulomb's law in your answer for this again. So, like I said, claim evidence reasoning, very, very important. I'll see if I can maybe throw up a video about that at some point in time. But you get the idea here. The more specific you are in regards to Coulomb's law and the explanation is about the attraction to the nucleus, the better off you're going to be. Just make sure you're using the right explanation. If you're comparing two elements in the same group, use the distance from the nucleus to the outermost electrons. If you're using elements in the same period, utilize magnitude of charge. So let's move on with our work with ionization energy, and let's consider what the outermost energy level of an ion is when compared to the neutral atom if we're looking at ions in and of themselves. So let's write out some electron configurations, first for zinc and then for zinc 2+, and let's think about what's going to be easier to remove an electron from. Well, if we look at zinc, zinc has its outermost energy level, or outermost electrons, in the 4s sublevel, whereas zinc 2+ has its valence electrons in the 3d sublevel. So the justification here is very similar to that when we compare elements in the same group. It's much easier to remove an electron from the 4s sublevel than the 3d sublevel. Thus, zinc 2+ has a higher ionization energy because the 3d electrons, which is where the valence electrons would be removed from, is much closer to the nucleus than that of the 4s sublevel. So you have to keep in mind when you're comparing ions that you can't use magnitude of charge of the nucleus because they're both zinc atoms, right? There's both ions of zinc. So as a result, the magnitude of charge in the nucleus doesn't change. Zinc has 30 protons and zinc 2+ has 30 protons. So we really need to look at where those outermost electrons are. The further they are away from the nucleus, the easier they are to remove and thus a lower ionization energy. The closer they are to the nucleus, the harder they are to remove and thus a higher ionization energy. All right, so with that being said, a couple of other questions I wanted to throw your way. We've got, I think, 3 more, maybe 2 more. I'm not exactly sure. We got a few more questions I want to take a look at, and then we will wrap this fairly long video up here in just a moment. But go through, take a look at this, and think about how you would go about doing this, and we'll be back here in just a moment. So for this type of problem, I actually had to break out a periodic table so that way we could kind of figure things out. But what I'm going to do is I'm just going to write the endings of these electron configurations here because it asks us, find the atom that only has 1 electron in the highest occupied energy sublevel. So we're going to need to actually do the orbital notation for this. If you remember orbital notation, your orbitals are lines like this, and then you have up and down arrows that you fill in. I didn't fill that in correctly. Up, 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 down, down, down. And it says only 1 electron in the highest occupied energy level. So let's go through and write out the ending of this electron configuration. So S is going to end in 3p4. Calcium ends in 4s2. Gallium ends in 4p1. I think we have our winner here, but let's keep going. Antimony ends in 5p3, and bromine is in 4p5. So the one that has 1 electron in the highest energy level is the one that has 1 electron in the highest energy level. I don't know how else to describe it, but gallium is the correct answer for that one. So pretty straightforward. Let's move on. All right, so we have another practice problem here. It says the effective nuclear charge experienced by the outermost electron on Na is different than that in Ne. This best accounts for which of the following? So let's think about the charge that's experienced in Na when compared to Ne. So the outermost electron of Na is in the 3s sublevel, and Ne is in the 2p sublevel. So very clearly, the outermost electrons in neon are going to experience an increased attraction, whereas the ones in Na are going to have a decreased attraction. So let's think about how this might play a role here. It says Na has a greater density. Well, we haven't really talked about density. In fact, it was so exciting that I accidentally left it there twice. Na has a lower first ionization energy. Well, let's think about that for a second here. Na has a lower first ionization energy of that of Ne. Well, the Ne valence electrons are going to experience greater attraction. So the ionization energy is going to be really, really high because of the greater attraction. Na Its valence electrons are in the 3s sublevel, so less attraction, lower ionization energy. So there's your answer. So it's talking about nuclear charge, it's talking about attraction between the outermost electrons in the nucleus. You can really use that as a way to justify ionization energy. So again, just something else to kind of think about as we move forward. And then lastly here, it says atoms of the element X have the electron configuration shown above. The compound most likely formed with magnesium is. So remember how compounds form. We look at our charges, right? So we know magnesium, based on its periodic table location, has a 2+ charge. And remember, we cross and drop. So the 2 goes down on the bottom right-hand side, and then whatever charge the other element is becomes the subscript on magnesium. If they're the same charges, or opposite charges of one another, that is 2 plus 2 minus, they cancel. If we can reduce, we try to reduce it to the lowest whole number ratio. Anyways, I need to figure out what this element is. So if I look up 3p3, I'm going to find out that that is phosphorus. And phosphorus here has a 3 minus charge. So when we cross and drop, we end up with Mg3p2. So there you go. Answer choice E is the best answer here. So again, there's lots of different ways to ask questions about this particular topic, and I would be remiss if I didn't try to go through as many as I can. Unfortunately, I can't go through all of them. So take your time, really become well versed in Coulomb's law, and hopefully you won't run into any significant issues. As I mentioned before, if you like this video, feel free to comment, subscribe, like the video. It really does help me out. I'm just trying to get as much chemistry content out as I possibly can. I really appreciate your time today. Thank you so much for watching. Hopefully you learned a little bit, and if you did, well, good on you. We'll see you next time. Bye, everybody.